Hello, everyone. It's Mr. Kablan here, and today and for the next couple of lessons, I will be presenting what a topic called optimization. And today, what we're going to start off with is dealing with optimization, dealing with area and perimeter of rectangles. So let's get right to it over here. What we're going to see in this chapter is that when we're dealing with optimization, we are going to deal specifically with the measurements that maximize things like maximize the area as well as to minimize the perimeter. That's actually what we're going to do in today's lesson. And what we're going to see in future lessons that when we maximize or optimize volume, we're going to maximize the volume and minimize what's called the surface area. Okay, so that's what we're going to cover overall in this particular chapter. So today what we're going to look at, we're going to look at a couple of investigations here in terms of how we can determine the dimensions of something of rectangles that maximizes the area and minimizes the perimeter. So when we're dealing with that, the main thing we're going to do here is we're going to do a couple of investigations based on measurements, and we're going to discover that when we're optimizing perimeter and area, that a certain shape will appear in every single investigations. Okay, so rectangles with the same perimeter can have different dimensions or measurements and contain different areas. And what we're going to discover is that when we look at that, okay, a certain shape is going to give us the optimized measurements. And basically what we're going to see in this first investigation is that rectangles with the same area can have different dimensions and different perimeters. Okay, so that's what we're going to focus on in today's investigations. And we're going to look at rectangles with where all four sides are enclosed, as well as three-sided figures as well. All right, for the first investigation here, it says here that many rectangles have the same perimeter, but have a different area. So what we're going to do in this chart here is we're going to determine the length and width of a rectangle that optimizes the measurements. So what we have to do here is to understand the fact that for this first investigation, that the perimeter of each rectangle we're going to look at in this investigation will be 16 centimeters. Now, the first example is given to you here, and you're probably looking at the numbers and asking yourself, well, how do we get those numbers? So what we're going to do for the first two investigations is to do a calculation, and we're going to discover a pattern based on the information that we're going to do from the first two calculations. So the first thing we're going to do here is we're going to look at a length of 1 and a width of 7 and determine how we can figure out where those numbers come from. Now, when we're looking at the length will be provided for you. So what we want to do here is discover how we can calculate the width, okay, and the area. And let's deal with that. So what we're going to do for the first one over here is take a look at how we can use the perimeter, okay, as well as a length of 1 to determine the width, which we're going to discover to be 7, as we saw on the chart here. All right. So step number 1 here. Always start off by writing down the formula. Again, the formula for the perimeter of a rectangle is 2 times length plus 2 times width. Okay, which tells us that the two lengths are the same length as well as the width, the same measurement. Sorry. All right. So what we're going to see here is that we know that the length of 1 is going to replace the L. So we'll start off with that. And the perimeter of 16 is going to replace the P. So in the next step here, we're going to have 16 is equal to 2, and in brackets 1 plus 2w. Now you can see on the right side here, what we have here is a 2w that we're going to solve for in a sequence of steps here. So the next thing I'm going to do here, I'm going to take this 2 and 1, multiply those two together. And then since we want to leave the w alone here, I'm going to take this 2, and then we're going to move it to the other side and subtract it from the 16. And that's going to give us 16 minus 2, okay, which gives us 14. And last but not least here, we're going to divide both sides here by 2, okay, to cancel out the 2's on the right side, okay? And as you can see here, what we have here is w is equal to 7, all right? So if we go back to the chart here, okay, you're going to see here, sorry, you're going to see that in this particular section over here, when we go back, okay, what we have here, okay, is indeed what we have here is a width 7, which we discovered in the last slide over here. Now for the area, all we have to do is multiply the length and the width, which is 1 times 7, and then that's going to give us an area here of 7 square centimeters. All right. So the next thing we're going to do here for number 2 is we're going to calculate the length. We're going to use the length of 2, okay, to determine the width. Okay, so we're going to approach it the exact same fashion. Okay, keep in mind that the perimeter is still 16. The only thing that we're going to change up is the length of 2 and then figure out what the width is. Okay, and then we're going to use that information to figure out the pattern. All right, so from here, okay, so in this case over here, we now have a length of 2, same formula. Okay, the only difference in this one here is the L is going to be replaced with 2. Okay, and the P here is still going to be 16. So you're going to see here that when we multiply the 2 and the 2, that gives me 4. And then we'll take this 4, move it to the other side, and then subtract it from the 16 that's already there. Okay, and then 16 minus 4 will give me 12. All right, and finally here, we're going to divide both sides here by 2. Okay, and this is going to cancel out the 2 2's on the right side here, and we will have a width of 6. So if you take a look at this chart over here, okay, you notice what we have there is a width of 6. Okay, and we're just going to do a rough sketch. Now the area over here is going to be 2 times 6, which gives me 12. Now what I want you to see here is the fact that we're increasing the length by 1, and you notice the width decreases by 1. Okay, so that's going to be the pattern we're going to use to fill in the rest. Now the area we're going to need to calculate as we go along as well. So with a length of 3, okay, since we're increasing the length over here, we're going to decrease the width by 1. So we have the length of 3 and the width of 5. Okay, and then we get something. As you can see, when I'm drawing the sketch, I'm just trying to gauge you the general idea in terms of what's happening. Okay, so you notice what's going to happen over here is the length, okay, is increasing, and the width, okay, which is the vertical side going up and down over here, okay, is going to be decreasing. As I'm just drawing that just for the people that want to see it. Okay, and then when we multiply these two numbers together, we have 3 times 5, which gives me 15 square centimeters. Now, what you can see with the area over here, okay, the general pattern is that the area is increasing, okay, as we go down this chart. So last but not least, over here, you can see we have a length of 4, okay, so the next one here would be a width of 4 as well, okay, and the reason for that is you can see in the width column, it is decreasing by 1, okay, and then what we have here is this. Now, what we have here again is a special type of rectangle. It's actually not a rectangle. In fact, what we have there, if we have a length and width with the same measurement, okay, what we indeed have here is indeed a square, all right? And if you can see here that when we multiply the 4 and the 4 together, okay, what we have here is 16 square centimeters, all right? So what we're going to do here is answer the following questions and discover something about why we went through this particular investigation. So it says, which rectangle has the smallest area? So you can see here that one of the smallest areas, the first one over here, the long, thin, narrow rectangle here. And again, what we have there, again, when we're looking at a rectangle, it is clearly a rectangle. Okay, it has to be long and thin. All right, so the next one we have here is which rectangle has the largest area. And you can see that it's the last one here, it's rectangle 4. And we don't really have a rectangle here. And I mentioned a few seconds ago, what we have here is indeed a square. Okay, and it's a square because again, the length and the width are exactly the same. Now, keep that in the back of your mind as we go through these investigations, because there is a general idea that I want you to see for each investigation that you see here. All right. So the next thing we want to do here is to just draw a conclusion in terms of what we came up with in this investigation. So it says draw a conclusion in terms of what type of shape would give the largest area. Okay, as you can see over here, what we would have here is a square, and it would yield the largest area. Okay, now this is important again in terms of real life applications, because if you look at most buildings, especially when it comes to the floor, okay, and my classroom is a perfect example of that. So if you look at the floor, you will notice that every single tile, okay, is a square. In fact, each square is it has a length of 1 foot and a width of 1 foot. That's why when you're measuring the space of something, okay, or the area of a room, especially in a retail and things like retail, okay, that's how they determine how big something is. It's based on the square feet in particular. Okay, so that's how you can figure out or estimate how big something is in terms of area. All right, so the next investigation we're going to look at, we're now going to deal with it in a similar fashion, but this time we're going to be given an area and we're going to discover something about perimeter. So it says here, it says many rectangles have the same area but different perimeter. Okay, so we're going to approach this the exact same way. The only difference in this case, as I mentioned before, is we're going to have an area, okay, of 64 square centimeters. And we're going to use the length that you see on the left side there, and then we're going to determine the width. Now, the calculation of that is actually very, very simple. Is that to determine the width, what we're going to do with each of these lengths is to take the area of 64 square centimeters and then divide it by the length. So, for example, for this first one here, with a length of 1, okay, to determine the width, all we need to do here is to take the 64, divide it by 1 to give us 64, okay? Now, the perimeter itself is using the formula for perimeter, which is what we saw in the last screen there. And basically what we're going to do here again, if you put a length of 1 and the width of 64 into the formula for perimeter, okay, you will discover that what you have there is 130 centimeters, okay? And we're going to see that calculation in full steps there and then for the next one. So for a length of 2, okay, to determine the width, you're going to take 64 and then divide it by 2. So 64 divided by 2, that's going to give me 32, okay? Now, for the sketch, again, I want you just to generalize what's happening to the shape here. As you can see, the length is increasing, which is the top part over here, okay, and the width is decreasing. Now, when I use the perimeter formula here, okay, we're going to take the length and the width, okay, length plus width, add them together, and that's going to give us 34, and 35, 4 times 2 gives me 68. Okay, so the perimeter of this shape over here is 68. Okay, now you can see, just compare the first perimeter to the second one. Notice it dramatically decreased. Okay, so you're going to see the general pattern of the perimeter, okay, is going to decrease as we go along. But again, the general idea for this investigation is to discover what shape we really have with a perimeter that happens to be the lowest. Okay, so the next one here, we have area of 64. Okay, we're going to take the 64 divided by 4, which gives me 16. Okay, as you can see here, again, just to do a sketch, okay, the length is increasing and the width is decreasing. Now, when we take the perimeter of that, okay, what we have here again is a perimeter of 40 centimeters. And again, as we scroll down the perimeter column, as you can see, the perimeter is decreasing. All right, and then last but not least here, and I chose these numbers specifically, we're going to take 64 and we're going to divide that by 8, and that's going to give us 8. Now you can see here we have the length and the width, which happens to be the same, and surprise, surprise, what we wind up getting there is a square again. Now you can see here the reason why we did this in different investigation is you can see that even though this is a different investigation, the end result is the same in terms of the shape. Okay, and what we're going to see here with the perimeter is that when we find the perimeter of this, notice that what we have here is something that has the smallest perimeter of all the 4 shapes that you see here. Okay, so again, which rectangle has the smallest perimeter? And as you can see, it's this last one. Okay, and what we have there is a square. Okay, and again, which rectangle has the largest perimeter? Okay, it happens to be the rectangle. Okay, so when you're looking at a shape, okay, anytime that you're dealing with the largest area, which we saw in the previous example there, okay, when the area is maximized, okay, the perimeter is minimized, and that's what you see in this example. Okay, so the general thing I want you to see here between this investigation and the last one, as I said before, is the fact that what we have here is indeed a square, which optimizes the measurements. Okay, so draw a conclusion about what type of shape would give it the smallest perimeter. Okay, and as I said before, squares gave us the largest area with the smallest perimeter. Okay, all right, so that's dealing with the rectangles there. And again, in order to maximize area and minimize perimeter, the shape must be a square. So square keeps popping up in every single investigation. All right. Okay, so the next thing that we have here is we're now going to look at, again, perimeter and area relationships of a rectangle. And we're just going to do similar investigations as well. And what we want to see here is that one of the investigations we're going to look at is very similar to the ones that we saw in the previous slides over here. And we're also going to look at what happens when we take a look at a 3-sided figure, which is going to be once relatively challenging because we actually have to make up a formula for that, or so should I develop it? Okay, so we're going to look at that as well. And basically what we want to see here is it says determine the dimensions of a rectangle that will maximize the area and enclosure of a perimeter of 24 meters. So what we're going to do from this one over here is that from the previous slides over here, what we knew is that in order to maximize the area and minimize the perimeter, okay, the shape must be a square, okay? And this is what's called optimizing, okay? And what we want to do here is to figure out that when you're looking at perimeter, okay, what we have here, okay, as you can see, is a square. Now remember that a square has all four sides which are the same. So what I'm going to do here is that I'm going to let S represent each side of the square. So starting off with the top, that's an S, this is an S, and this is an S, and this is an S. Now remember the definition of perimeter is taking all the sides, okay, and adding them up all together, okay, or the sum of all sides. Okay, so all you can see here is I've taken the four S's, okay, and I'm just going to add them together. And we have here a formula of P perimeter is equal to 4S. Now what this means here is if I wanted to figure out the perimeter of something, okay, and where all sides are all the same length or same measurement, I can use this formula. And you're going to see that we're going to use this formula to actually work backwards where we can find the side lengths with a given perimeter. So for this question over here, okay, notice it says here, determine the dimensions of a rectangle that that will maximize the area of an enclosure of perimeter of 24 meters. So all we're going to do here is take the perimeter of 24 and replace the P. Okay, and as you can see, if we have a perimeter of 24 and we want to figure out the side length of each one, all we need to do here is divide both sides here by 4. So this tells us here that if a square has a perimeter of 24 meters, each side will be 6 meters long. Okay, so that's an example of optimization where, again, the area is maximized, okay, and the perimeter of 24 is the minimized perimeter. All right. Okay, so the next thing what we want to do here is calculate the area, and all we're going to do there is to use length times width, very simple formula. So in this one over here, 6 times 6 is going to give us 36 square meters. All right, so that would be the actual value of the maximized area with a perimeter of 24 meters. Okay. All right, so the next thing we're going to do here, we're now going to do a three-sided rectangle with a fixed perimeter. And what we want to do for this one over here, again, is to do the chart first so you can understand how we're going to develop this here. Now, what I want you to see here is the fact that we now have a three-sided figure. Now, if you look on your formula sheet, okay, unfortunately, we do not have a formula for a rectangle with only three sides. So we're actually going to develop it using basic terminology. Okay, and that's exactly what we're going to do in the first step here. All right, so when we take a look at that, and what I want you to see here is that we're going to use the diagram to help us to develop a formula over here. So what we know about the perimeter of any shape, okay, especially, or so should I, shape with straight sides, is that the perimeter is always the sum of all sides that make up the shape. Now, as you can see, using the diagram there, we only have the three sides. We have the two widths, okay, on the left and right respectively, and the length on the bottom. So we're going to develop the formula using just that. Okay, so you can see that what I have here is W plus L plus W. Now remember back in chapter 3, we discovered collecting like terms, and that's exactly what I'm going to do in the next step. So when I add these two W's together, that's going to give me 2W and then 2W plus L. All right, so that's going to be the formula of a three-sided rectangle. Okay, now by doing that, okay, in order to figure out the length, okay, for a three-sided figure with a width of 1, we're going to use this formula to solve for that. So what we're going to do first, we're going to take the width of 1, replace it in for the W, and we're going to take the perimeter of 24 and replace it in for the P. So what we have is something that looks like this. Okay, now you notice on the right side, we have the L by itself, and we're going to isolate it algebraically. So 2 times 1, that's going to be 2. We're going to leave the L alone. So we're going to take the 2 and then move it to the other side and subtract it from the 24. So you can see here that when we have a width of 1, okay, with the perimeter of 24, that's going to give us a length of 22. All right, so sorry, just to go back to that. Okay, so if we take a look at this one in particular, okay, that's the example of the first one over here, which was given to you. Okay, and then length times width would be 1 times 22, which gives me 22 meters squared. Okay. All right, so the next thing we're going to do here, we're going to use a width of 2, And we're going to do this calculation to see that we can actually develop the pattern based on the length and see what happens when we have a width of 2 and solve for the length. And we're going to do exactly that. Okay, so for a width of 2 and a perimeter of 24, again, perimeter remains the same. We're just changing the value for W here. So we're going to take the 24, place it in for the P, okay, and then 2 times 2 here is 4. And we're going to solve for the L by taking the 4, moving to the other side, and subtracting it from the 24 that's already there. And as you can see here, that's going to give me a length of 20. Okay, so going back to the chart over here, okay, notice what we have here is that the length is decreasing by 2. Okay, now for the area, we have 2 times 20, which gives me 40. All right, now you're going to see here that as we take a look at the lengths over here, the lengths will all be decreasing by 2 as the width increases by 1. Okay, so we have 4 and 16. Okay, so I want you to see that it is decreasing here. And all I'm going to do for the area is multiply the two numbers together. So we have 4 times 16, that's going to be 64. So if I width of 5, that's going to be a length of 14. Okay, and last but not least, we have a width of 6 and a length of 12. All right. Now, the key thing I want you to see here is that we're going to use this information to answer the following questions, and we're going to discover a relationship between width and length of three-sided figures. So what are the dimensions with the optimum or maximum area? Okay, so as you can see here, if you look at this chart over here, the biggest area is this last one of 72 square meters. Okay, now what I want you to see here is to take a look at the values for width and length and discover that there is a relationship numerically in terms of what we need to do the width in order to get the length. So what we have here again is indeed a rectangle, okay, where the length is much longer than the width. Now I want you to take a look at the numbers specifically over here and ask yourself, how do I go from 6 to 12? Well, if we're thinking about multiplication, okay, you should be able to discover that if I take this 6, okay, and then multiply it by 2, or simply just double it, that will give you 12. Now that's going to be important here because that's exactly the relationship of width and length of all three-sided rectangles. Okay, so as you can see here, the length is twice as long as the width. So for the 3 stars here tells us the relationship here. So for a three-sided rectangle with a maximum area, the length is 2 times longer the width, and that's always going to be the case. Now remember back in the previous slide over here, okay, we developed the formula in order for us to discover that. Now what we want to do for the next one over here is to actually take a look at that formula, okay, and then develop another formula that's going to help us understand to figure out specific dimensions for a three-sided rectangle here. So it says given the formula P is equal to 2W plus L, where L is equal to 2W, develop a new formula to determine the measurements of three-sided rectangles. All right, so step number 1, we're going to start off with the basic formula. Okay, and what we're gonna do here is we're gonna do something a little bit tricky, and it's gonna be hard to understand at first here, but we're going to develop a formula based on the fact that we have this formula in front of us, and we know that the length is 2W. So all we're gonna do here is we're going to take this L, okay, and replace it with 2W, okay, and the way we can do this again is understanding that based on what we saw in the previous investigation is that the length is always twice the width. So right now, when I replace this L with 2W, I get something that looks like this, all right? And for the last step, we're just gonna gather the two terms over here, and we get P is equal to 4W, okay? So what we're gonna do next over here is we're now going to use this formula, P is equal to 4W, to figure out the dimensions of a three-sided rectangle with a specific perimeter, okay? So for the last example here, it says a DJ booth is situated behind a dance floor as pictured, okay? And the dance floor's perimeter is surrounded by 44 meters of rope. So what that means is that the three-sided rectangle you see on the screen, okay, the one that's colored in white over here, okay, when I add up these three sides over here, okay, it's going to give us 44 meters. Now, the way we're going to do this is we're going to use the formula we developed, okay, from this slide over here, okay, to discover the answer over here. Okay, now what we have to do first is understand that we need to calculate the W, and then from there we're going to see how we can calculate the length, okay, using what we did in the investigations in the previous examples here. All right, so step number one, we're going to take this 44 meters and replace it in for the P. Okay, and for the final step here, we're going to divide both sides here by 4. Okay, and this is going to give us a width of 11. All right, now remember that for three-sided figures, the length is always twice the width or double the width. So for the last step over here, to figure out the length, all we need to do here is to take the width and multiply it by 2. Okay, so for a three-sided figure that has a perimeter of 44 meters, okay, that's going to give us a width of 11 and a length of 22 meters. All right. All right, so that wraps up the first lesson on optimization, and I will see you at the next one.